first part of chapter 11 that we're going to talk about is neuron function, and this links really well with muscle contraction. So these are the receptive ends of the neuron, this is the body, and then this is the flow of information. We've already seen these axon terminals at the bottom. We saw that these make up the neuromuscular junction along with the muscle fiber cell. I want to take a step back for a moment and make sure that we realize the difference between the spinal cord that we'll talk about in chapter 13. So this is the superhighway, how your brain receives information. So information goes down or up in your spinal cord to or from your brain. Coming out of the spinal cord, we have nerves. Nerves are made up of bundles, and guess what? We call them fascicles again. Inside the fascicles, there are nerve fibers that are bundled. So each one of these that I'm putting an X on, that is actually a neuron. So nerves are bundles of neurons. Like many cells, neurons have a resting membrane potential. They're highly irritable. They respond to stimuli by generating an action potential. The impulse is always the same regardless of the stimulus. Let's look at some of the membrane ion channels. So the chemical gated means that a chemical is going to open the gate when it binds. Neurotransmitter like acetylcholine. So what happens when acetylcholine binds the acetylcholine receptor during excitation? We had what? Sodium come in and we had potassium trickle out. That's a chemical gate. Then a voltage gate. You remember when we had sodium only gate? So this happened, the chemical gate happened, was activated. That caused the inside of the cell to become more positive, and then this sodium only opened and sodium came rushing into the inside of the muscle fiber cell. The last gate is called a mechanical gate, and it responds to physical movement or deformation of the receptors. When gated channels are open, ions diffuse quickly. We know they move along their concentration gradient. If I have a bunch of sodiums on this side and I don't have any sodiums on this side, the sodiums will move from high to low. Remember diffusion? Along electrical gradients towards opposite electrical charges. Remember, it's positive on the outside, but it's also negative on the inside. So they're moving from positive to negative. This ion flow is what creates a current. This voltage change across the membrane is what causes depolarization. So these are the exact same concepts that we learned in skeletal muscle. We're just now applying them to a neuron, and you'll see a few places where it's a little bit different. Here's one difference. In a neuron, the resting membrane potential is -70. It was -90 millivolts in the muscle, right? So the membrane is said to be polarized. It's still negative on the inside and positive on the outside. Now we have another similarity. What's on the extracellular side, outside? Outside of a neuron, there's more sodium. Inside, there's more potassium. Remember, we also have these really large negative proteins that make the inside more negative. Remember in skeletal muscle, when we talked about excitation, we had an end plate potential, and then we developed an action potential. Here in the neuron, they call it a graded potential and then an action potential. But you can think of them very similarly. A graded potential is just something that's happening locally. Remember, this is end plate potential. It was happening locally at the neuromuscular junction. So again, a similarity. We have depolarization, which the interior of the cell becomes less negative. But we have something new called hyperpolarization. So increased polarization. It would be if you had -70 millivolts and for some reason the inside of the neuron dropped down to say -90. It would make that neuron much harder to fire the next time. It would have to overcome this 20 voltage difference and then still make it to threshold. Let's look at generating an action potential in a neuron. So in the resting state, we have a resting membrane potential. It's at -70 millivolts. The sodium and the potassium channels are closed. You may have some leakage occurring, but the main gates are closed. Step 2, we have depolarization. All of this should seem familiar to you. So sodium gates are open, sodium rushes into the cell. This causes depolarization, which opens more sodium channels. The inside, the resting membrane potential becomes less negative. If it reaches threshold, which is -55 to -50, it's going to cause all of the sodium channels to open. The rush of sodium coming into the neuron creates a +30 millivolt spike or jump, and this is going to produce the action potential. Step 3, we have repolarization. So the sodium channels are inactivated, the potassium channels are open, and we're going to see the potassium channels allowing potassium to exit. The repolarization returns the membrane to its original resting membrane potential. So this is the new term, hyperpolarization. Sometimes the potassium channels remain open a little bit longer, and this causes the potassium to leave, and it makes the inside of the membrane become more negative than the resting membrane potential. We call this hyperpolarization. Let's look at this figure and kind of talk about the spike that we're seeing here. So this would be the -70 millivolt resting membrane potential. Let's say threshold is about here, and threshold is if we get above, say, -55 millivolts. So this area right here is when a few sodium gates are open. Once we reach threshold, this is when all the sodium gates open, and we generate our action potential. When we start going back to repolarization, this is when potassium leaves. And do you see how the potassium, extra potassium, has left and has made the resting membrane potential drop below -70? Let's say it's at -80 millivolts. That would be hyperpolarization. It's extra negative. Just like relaxation or repolarization reset the skeletal muscle, it also resets the electrical conditions, but not the ionic conditions. So we still have to have the sodium-potassium pump, making sure that the sodium gets back to the outside and the potassium gets back to the inside. Now we move to the steps. So you should be able to explain this. When the neuron is stimulated by chemical, light, heat, or mechanical disturbances, what's the difference here? This is a neuron action potential. It can be stimulated by chemicals or light, like in our eyes, photoreceptors, or by heat, temperature receptors. Muscles were stimulated by a neuromuscular junction, right, by a neuron. So this is a neuron. We're talking about an action potential developing inside the neuron, and it can be stimulated by various events. But this part's the same. Sodium rushes in to the dendrite region or the soma region. I'll show you in just a moment. The sodium diffuses for short distances on the inside of the plasma membrane, producing a current that we call a local. So it is local depolarization. You could also think of local as kind of graded, if that helps you. We talked about graded potential. We said graded potentials travel over short periods. They're kind of referred to as local potentials. So voltage across the membrane shifts from -70 towards 0. The trigger zone is the area where you find the threshold. So if you reach this trigger zone, then we're going to see this local potential shift into an action potential. So you can see that the inside is negative, the outside is positive. What's going to happen when you have a stimulus? Gates are going to open and you're going to see sodium coming in. That sodium is going to cause the inside of the membrane to shift from negative to positive. So where does this occur? Here's the neuron. This is the body. sometimes called the soma. We'll talk more about it as we move into the next unit when I add the rest of chapter 11. So this is the body. These are the dendrites. Here is the axon and the axon hillocks. This is the trigger zone or threshold. Here is the axon. The message goes down the axon to the axon terminals. So where would you find a local potential? It occurs in the dendrite or the soma. So locally, this neuron is going from negative 70 millivolts up to a higher voltage. Some local potential characteristics. One, they're graded. You need a really strong stimulus to open all of the sodium gates and get to threshold. So a weak little stimulus isn't going to do anything. Decremental, meaning that the signal, the local potential, gets weaker the farther it's spread from the point of impact or stimulation. They are reversible. So you can create a local potential and then stop and not have an action potential. So think about it, you're priming your neuron, you're getting ready to do something, and then at the last moment you change your mind. So if you have a local potential, you do not have to have an action potential follow it. And some nerves can use these local potentials to either excite or inhibit another nerve. So say you wanted to send a signal, one nerve wants to talk to another nerve, then you would be exciting that neuron, the second neuron. There might be a time where you want to inhibit a neuron. And this will get a little more complicated as we move through the brain chapter and the central nervous system, but we'll get there. This figure is trying to explain all of this to us again. So here's negative 70 millivolts. This is resting membrane potential. This section right here, this is when some of the sodium gates opened. If the sodium causes a local potential, then we're going to reach threshold, and we're going to have tons of sodium entering the neuron, and it creates an action potential. On this side, we're going to have the potassium that's exiting and bringing the neuron back to the resting membrane potential. You can see this is a good example of hyperpolarization. This is the negative 70 line. You can see for a brief period of time that the neuron dips below the negative 70 resting membrane potential to, say, negative 80 millivolts. Here are the second set of steps for action potential. So if the threshold potential is reached, voltage sodium gates open in the axon hillocks. There's a flood of sodium that causes depolarization, or the inside of the neuron reaches the positive 35 millivolts. Only then will the neuron fire. The depolarization will spread down the axon and cause the axon terminals to release a neurotransmitter. The sodium channels will close, the potassium channels will be open, and that'll cause repolarization of the cell. And when I say cell, hopefully we know now we're talking about the neuron. So this is where the axon hillocks is located. So this is threshold. When these sodium gates open at threshold, we go from negative 55 millivolts up to positive 30 or 35 millivolts. That causes the message to spread down the axon and causes the axon terminals to release their neurotransmitter. So this is called action potential propagation. So once we reach threshold, which is negative 55, tons of sodium gates open and the message is destined to reach the axon terminals at the end. In this figure, they're measuring right here at this electrode point. At this electrode, the neuron is at resting membrane potential negative 70. Here comes the action potential. It's being propagated or moving along the neuron. So you can see when we get to the node where we're measuring, we can see that the inside has become more positive. This is the generation of an action potential. Then the area directly behind the action potential is recovering. And we call that hyperpolarization, or where it became slightly more negative. Some more characteristics of action potentials. The neuron response begins at the dendrite, travels through the soma, down the axon, and ends at the axon terminals where it's going to release a neurotransmitter. We call this the all or none. So either an action potential happens or it doesn't happen. It doesn't halfway happen. So once you reach over the threshold, once all of the sodium gates open at the axon hillocks, the action potential is going to happen no matter what. Even if you change your mind, the action potential is still going to occur. The axon terminals are still going to release the neurotransmitter. That propagation allows the axon potential to be transmitted down the entire length of the axon towards the terminals. It doesn't get weaker. We want it to get to the axon terminals. Why? Because they're going to release a neurotransmitter. And action potential is irreversible. A lot of people refer to this as shooting a bullet out of a gun. You can't put the bullet back into the gun once you've fired it. So an action potential is all or none. How does your brain, how does your central nervous system tell the difference between a weak stimulus and a strong stimulus? Basically, it's going to look at the frequency or the number of impulses that are being received. So the higher the frequency means stronger stimulus. Basically, the stronger the stimulus, the more action potentials are created. There's something called refractory period. It's a time in which a neuron cannot produce another action potential. It's almost that the neuron has to reset itself before it can fire again. So we're going to look at absolute refractory period and relative refractory period. This figure is showing you absolute refractory period. It basically corresponds to the generation of an action potential. If the neuron is generating an action potential, it cannot generate another action potential right this very second. Then there's this repolarization phase where we call relative refractory period. So if you want to link absolute to this is action potential development and relative refractory as repolarization here. So this is when the neuron is resetting itself, right? It's going to hyperpolarization. So again, the neuron cannot fire in these two areas. So we have to wait till it gets out of hyperpolarization, -70, for it to normally have another action potential generated. There are some exceptions to this, but we'll talk about those later. Last couple of slides, we need to talk about the rate at which the action potential is propagated down the neuron. So how fast does the action potential travel? Well, there's two factors. One is the axon diameter. How thick is the axon of the neuron? The second is the degree of myelination. We haven't really talked about myelin yet, but this is a covering that helps with conduction. So it's basically insulation on a neuron. So there's continuous conduction and there's saltatory conduction. Continuous conduction is non-myelinated. So you've seen the other figure where we had the myelin wrapping around the neuron. This is non-myelinated. So this section is undergoing action potential right now, or propagating action potential. This side is at -70 millivolts resting membrane potential. Basically, this section is going to finish the action potential and it's going to cause the next section. So that's what we have here. The next section is forming an action potential, while the previous section, it was in action potential, now it's in the refractory period. And then eventually the refractory period turns into the normal resting membrane potential or excitable membrane. So basically the action potential is spread or propagated down the axon of the neuron. In saltatory conduction, we have myelinated neurons. So this is the myelin. And basically this is kind of playing hopscotch. So here's the action potential. It goes through the myelination, comes to this area that's at resting membrane potential. Well, guess what happens to this area? It now becomes excited and the sodium channels are going to open. Well, what happened to the section that was doing an action potential? It's now in refractory. Now this section is going to go through the myelin and cause the next section to have an action potential. What's going to happen to this previous section? It's going to go to refractory. What happens to this previous section that was in refractory? It's now in resting membrane potential.